of is that if this is a particle trapped inside a potential warp, if you want to kick it from the ground state, this is called the ground state, to the next level up, okay, you need so much energy to kick it up. And if you want to kick this state to the next level up, you need so much energy to kick the energy of the system. Okay? And each packet of energy that you need to inject into the system to kick it one level up is given by this amount, like the energy of a photon. Okay? And that is the characteristic of the simple harmonic oscillator. And another thing that you should take note of is that these particles are very strange actually. If you think of this square of these wave functions as the probability of finding the particle in this warp, you find that they are equally likely to be found anywhere. If you were to square these wave functions and try to look for the particle is equally likely to be found anywhere. That is not the classical picture that we have. We have a simple harmonic oscillator. We think of that particle as being sometimes here, sometimes there, and sometimes it's more likely to be found here, sometimes it's more likely to be found there. But these energy states, these are eigenstates of this equation, okay, may have the property that the particle is equally likely to be found anywhere in the world. They are likely to be found anywhere, not at a preferred location. Okay, that is a non-classical behavior of these eigenstates. Okay, and then if you go to higher energy state, you will find that it will oscillate more, and the particle is equally likely to be found anywhere in the world, not like in a pendulum. Okay, because we know that this is the quantum description of a pendulum, and it does not look at all like a pendulum. Okay, it does not look at all like a pendulum, and that's no good, right? Where is the classical picture then of a pendulum? This is like a pendulum, and we are not seeing that. Another thing that is very amazing about this oscillating system is that at the lowest energy state, the ground state, there's still some energy involved with this ground state at the lowest energy state, n is equal to 0. So if you try to bring this oscillator to rest, you don't do anything to it, you don't give it energy. The quantum mechanical description of this particle is that there's still some energy associated with that. Okay, you don't give it any energy, you don't just let it rest at its most quiescent, lowest energy state. There's still some energy associated with that. Okay, and you find that photons would be the same way in the future. We are not getting there yet, but that photons have this ground state energy level that's non-zero. Okay, so there's another thing that you should know, and that so when there's nothing, there's something. In quantum mechanics, when there's nothing, there's something. So if you let this rest in this quiescent state, there's supposed to be no photons there, no energy there, nothing there, but there's something. That's what this means. Nothing is something. Okay. So nothing is something, and that if you have a quantum harmonic oscillator like an electromagnetic field, and if you cool everything in the universe down to 0 temperature, there's still a vacuum field, electromagnetic field, in the system. And that vacuum field is always there. And that vacuum field has that energy. It fills the universe with it. Okay? If you can harvest the energy, it would be wonderful. There would be no energy crisis in this world. Okay? We don't know how to harvest that energy yet. Okay, this is the lowest ground state energy. I guess I can start on something new, but maybe not at this point. Maybe not at this point. But I'd like to further say that if you have this kind of thing, this are the called energy state. The fact is that they solve this eigenvalue problem. Okay? And if you were to look at the time behavior of this energy state, as we have said before, you just have to add e to the I omega n t, okay, to this thing. And you assume that this is the solution at t is equal to 0, and the time evolution of this energy state will be given by this. And I'd like you not to be confused this omega n. Okay, this omega n is En over h bar. Okay, it is given by this quantity over here, n plus half h bar omega naught over h bar. Okay, this can cancel each other. Or it's n plus half omega naught. Omega naught is different from omega n. Omega naught is the frequency of this spring resonance. Okay, omega n is a quantum frequency. It's a quantum frequency obtained from this, and dividing that by h bar. And then this is the time evolution of this. If you were to take this square value, the time dependence goes away. So if I were to take this energy eigenstate square, it becomes time independent. It becomes time independent, which means that if I were to think about those squares as the probability of finding the particle is not changing with time. It can be found anywhere within this world. This world, according to that function over there, is time independent. And that is not the picture we should have of a pendulum. In order to have the behavior of a pendulum, we have to linearly superpose different eigenfunctions with different time dependence. Say if we just superpose two of them, psi of dt is equal to e to the minus I omega 1t, psi of 1 z plus e to the minus I omega 2t, psi of 2z. And now if you take the square of this function, you will get a term that is proportional to psi 1 square. You will get a term that is proportional to psi 2 square. And then you get a term that is equal to the e to the minus I omega 1t, e to the plus I omega 2t, and then psi 1 z, psi 2 conjugate z, plus a term that is the complex conjugate of this one. You'll find that in this term over here, the time dependence cannot cancel. Okay? The square of this function, which is the linear superposition of two energy eigenstates, become a time-dependent function. And so if you just look at one pure energy eigenstate, they're time-independent, but if you add them up and superpose them, they become time-dependent because these two don't cancel each other. The time dependence is I omega 1 minus omega 2. As I said before, it's the difference that matters, not the absolute frequency that matters. So when you observe this from the outside world, you see the difference of the quantum frequencies. Those are the frequencies that matter. Okay? And I'll stop here, and then we can continue next time. I'll let Ayin lecture next time. Okay?